Okay, so yeah, we looked at the last chapter. We already looked at linear temporal logic, and then as a new language, and we looked at the nuXmv model checker so that we can formalize systems and transition systems mainly, and that we can then write specifications in linear temporal logic for these transition systems and also check them. When is the submission of the homework? Yesterday. Okay, so we should have done the survey this time. I forgot. Yeah. Okay. How was the homework? Yeah. Easy. Yeah.
The third one was okay. The last one was just at first we had some problems for some. I was just
Okay.
click for us.
Yeah. Yeah. That's If you you have to like get a bit practice and then find out which way to think about it. Yeah.
But then it was like okay, it was way much easier than we tried to do.
Okay. Yeah. Okay. And one thing I forgot to ask, so when you have these ones where you only have to write specifications and you don't need to code, do you still clone the project and run the tests locally, or do you just put them on GitHub and let GitHub run?
I run locally because it's fast.
Okay. Okay. Yeah, because we were thinking about maybe checking how many attempts people are doing until they get it right. But if you do it locally, we can't see it. If you do it on GitHub, we would see it based on your commits, right? Because each attempt would be a commit. But then we can't. It doesn't make sense to count the commits to see whether it was easy or not, right? If there's many commits, we could say it's hard because they needed many attempts. But yeah, we can't really measure it like that. Okay, good. Yeah. Okay. So you wrote some. Well, you didn't write many LTL specs, right? You mainly worked on writing the models and very, very simple LTL specifications. And how easy was it to read the counterexamples?
The second counter took me a little bit longer to understand it.
Okay. Yeah, I think, once you get the concept of counterexamples, it gets a bit easier. But then still, sometimes to actually relate the counterexample to the specification, you have to know both very well, right? You also have to know the specification very well to understand the counterexample and see why is it a counterexample and what does it actually violate or okay. Good. So now there are a few other topics which actually are quite relevant for practical applications. So one of them is the LTL specification patterns. And the motivation or general challenge is that this linear temporal logic and other temporal logics, they are very expressive, but they're often not very easy for engineers to read and write, or for users in general. It's quite a low-level language, like maybe assembly language. Already in nuXmv, we see that there are extensions of LTL, right? There are, for example, the extensions where you can write expressions with arithmetic, or write expressions where you assert the equality of variables, or a variable and a value. That wouldn't even be in the general LTL where you only have Boolean propositions, right? Those atomic propositions, they would just be Boolean variables. So we see that there's already a bit of a higher level language in nuSMV, but still it's difficult to write more complex relations that include timing in LTL. And here is an example of some relation between properties. So this property P is false between the properties Q and R. And then this is the LTL variant of it. So is that correct? Is this the right expression, or is it a wrong one? So what does the first part say? So this is a sentence in kind of natural language, right? Maybe it's a bit artificial natural language, but yeah, P is false between Q and R. So this P could be I don't know, maybe the robot is charging. So this would mean that the robot is unable to charge between maybe localizing the charging dock and driving towards it, right? So it might make sense to put this in a specification. But yeah, is this actually reflected here? So what is the first part of this implication? What does it say? It says that yeah, we need the survey. Yeah, this would be great. Yeah, thanks. So this first part basically, well, Q, this is the first event that we need to observe, right? We say between Q and R. So if, well, Q is there and we don't have R at the same time, but we will have R in the future. What does that mean? So right now, this doesn't have, well, let's kind of ignore the globally right now, but this Q means we have it right now because that's applied to the first time step in our computation. So right now we have Q. We don't have R right now, but we know that in the future we will have R. So that's kind of this between Q and R. So this means that Q is right now, and sometime in the finite future we will have R. Then this means that this implies that we will not have P until we really see R, right? So if this left side is false, how could this left side be false? Either right now we don't have Q, right? That's an easy way to make it false because that's the first, they're all conjunctions. So if the first conjunct is false, then this left side is false. So if the left side is false, this implies anything, so we don't care. Okay, so if we don't see Q right now, we don't care. If we see Q right now, but we also see R, because not R might be true, then we also don't care, because this means that the time between Q and R, there's actually no time between Q and R because they're both happening right now. Then it's also fine, because then it can't be between them because they happen right now. But let's say that we will never see R, because that's the only way to make this last conjunct false. So if we see Q right now, not R right now, but sometime in the future we will see R. Sorry, sometime in the future we will, no, never we will see R in the future. Then there's also no time between Q and R. So this means that here it says P is false between Q and R. This actually means that if Q and R do happen, so that's a bit different interpretation. You could also interpret it in a way that Q and R must happen, and that then P is false in between. So if we would use it with our charging example, that the robot cannot charge between locating the charging dock and being at the charging dock, then this would just say that it can't charge in between, but it doesn't require that the robot will ever get there, right? So yeah, this is maybe also something that in the natural language, it will be maybe a bit ambiguous. We don't know, does it get there, does it not get there? So we would have to look at the LTL constraint to see what it actually requires. So this is an easy LTL constraint because it doesn't have many operators, right? It only has 3 temporal operators, and the nesting depth is not very far. It's just depth 2. So this is the first level. And then these are nested within that first level. So this nesting here in the globally, this means that whenever Q is true and followed by R sometime in the future, then P cannot be true in between or must be false in between. So that's just wrapping this into a context. And there are some even simpler ones which are very, very popular. S responds to P. Maybe that's not so simple. Okay, S responds to P before R. Let's have a look at this. So if R happens, then this implies that if also P happens, then S must respond. So how do we say that S must respond? That while we don't see R, we will eventually see S. That's the kind of response. So if we know that R will eventually happen and P happens, then we will not see R happen before we see this S actually being present. Okay, so that's another example of something. So what could be a meaningful application of this pattern? So to make a meaningful application, we need to have something that stands for S, for P, and for R. Is there anything that would have this kind of temporal relation that this response basically means that we know that R happens, we know that then P happens, and then between that we must have S being a response to P. So what would make sense to be kind of a response? That's some obligation that if something happens, then something else must happen. So what are examples that something requires something else to happen in the future? If we think about the charging example, if, for example, the battery is low, then we should be at the, so let's say P is the battery is low. How do we respond to a low battery? Yeah, we go to charging dock. So S could be we are at the charging dock. Before what happens? Before the battery is completely empty, right? So maybe we could say that being at the charging dock is response to having a low battery before we run out of battery, right? Because then the robot would be in trouble if it runs out of battery before it's at the charging dock. Yeah, and then so if we eventually run out of that actually so maybe here this before R is maybe not this maybe that's like a high battery again, because this is the thing that we know it will eventually happen. So let's say low battery, going to the charging dock is a response to having a low battery before we can actually have a high battery again. That would make more sense. And then if we eventually want to have a high battery, this means and we have a low battery right now, then we can't have a high battery until we actually are at the charging dock. Okay, so now the question is, who came up with those things and what are they called? So the thing is that if you want to express some requirements of your system, they might be requirements like this, then you're the one who has to come up with those formulas, right? Because you need to encode them in LTL. So ideally, people thought, well, let's try to look for some kind of higher level language, because here, how many operators do you have? 1, 2, 3. Okay, not so many, but there are examples which have a lot more temporal operators in them. So we would like to have something more higher level to express this more easily, because these things are tricky to read, tricky to write. You can easily make mistakes. And that's why some researchers already like 24 years ago, 25 years ago, they started looking into a lot of LTL and CTL specifications. And they thought, well, is there something that we can recognize that people write over and over again? And they tried to find some patterns, so some expressions that occur in very, very similar combinations of operators. And that's what they called specification patterns, because they appear in specifications. They took industrial specifications of reactive systems, so systems that have these infinite executions. So, for example, some SMV specifications. And they looked at them and tried to identify what are some patterns that they could find. And on the higher level, they saw, well, there are some patterns which say that something must occur. And there are some patterns which do not require the occurrence, but they require some ordering of properties to be true. And then that's how they classified it, occurrence patterns. They say some state must happen during the system execution, and the ordering is about a relative order, so something happens before or after something else. And then they also realized that these different occurrence and order patterns, they also have some scopes. And we will have a look at what these scopes are. So they identified, out of all these examples, the scope global, so something that must always happen or always hold. And then they also have some, let's say, other temporal scopes. So before something else happens, maybe you have an occurrence of some other thing, or you have an order requirement on something else, or after something happens, or between, or this basically after something, and then it needs to hold until something else holds. So these are now global. That sounds like the globally operator, and that's maybe the easiest one of them, because you can just simply wrap the globally around that thing, and then you have your scope already defined. But other ones, these betweens and after, they're a bit more complicated. So they basically built this classification so that all of the patterns, they can occur in all of these scopes. It turns out that some scopes were very rarely used on some of those patterns that they found, but they basically always classified them into these scopes. And then for each scope, they looked at what are the further distinguishing properties of these patterns that they can find. That's, again, an illustration of the scopes, just like a visual catalog. So if it's globally, this thing needs to hold everywhere. If it's before R, then it needs to happen before the first occurrence of R. So R, of course, could occur many times, but here the before really says until the first occurrence of R, and the after also after the first occurrence of Q. We don't care whether Q occurs multiple times. And then in the occurrence patterns, they have one called the absence, so that something never happens. So this could be very common safety requirements, like that the two traffic lights are never green at the same time, right? We had this in one of the examples, and it's like this mutual exclusion. You could have it in other, like two processes never write to the same file at the same time, stuff like that you could write with this absence pattern. Or universality, that some part of the system execution only has states with this one property, and that maybe some system will always be available, something like that. And of course, these are kind of dual, because if you say something must always happen, it's like the negation of it must never happen. But still, they took it as two separate patterns in these scopes. Other ones, existence. So that's like the eventually, that the system execution must then contain some state. So for example, that this would be that maybe some computation must always terminate sometime in the future, or that some request must be responded to at some point in the future so that it's not left unanswered. Yeah, and then bounded existence, this would be that maybe between some states, there can only be a certain number of times that some property holds. So maybe, so we use this for some robots. Maybe the robot has to go from one place to another, and then this might be infeasible if the robot is blocked by moving obstacles too many times. So you might want to add an assumption that the robot is not blocked more than 3 times while it tries to travel from A to B, because then the robot can guarantee that it actually will be able to travel to B. Otherwise, if it could be blocked infinitely many times, it couldn't guarantee that it will ever reach B. But you might want to express that it reaches B. So that's why you need these maybe bounded existence patterns to say, well, we cannot block it more than 3 times for it to achieve its goal. Okay, and there are a few more on the order, so that in some regions of the system, so in some scopes that we can define, some states must be in order. So this one thing must happen first, and then the other thing, or even some chain of this happens first, and then that, and then that, and then that. Yeah, so the basic one, this would be some pair of states where first one thing must happen, and then only the other thing can happen. So maybe some machine needs to be turned on first before it can do something else, before it can operate. And these are, yeah, probably also some useful examples that you could imagine writing in some specification. Then this basic response, this is kind of the other way around. This one would be blocking the second event from happening before the first event. And the response requires that once the first thing happens, then the second one must eventually happen. So this is like the request granting. You could require that every request must be handled in the future, at some point in the future. What if, this is like in our traffic light example, we could say that whenever a car drives to traffic light A, then at some point in the future, traffic light A needs to turn green, right? Whereas, so what's the difference between then response and this precedence? If you say one thing must happen before the other. So let's take exactly the same thing. Let's take that the green light responds to a car. So if a car comes, a green light needs to respond to it. Here, the first event is again, a car comes. The second event is a green light. So now this one, precedence, would say that the green light can only happen if there was a car first. So it's kind of the other way around, because this one says that having a car must be happening before we have a green light. Okay, so what's the difference now? If you would have a traffic light that you have to implement, and you have those two constraints. So this one says a car requires that after some finite amount of time, there'll be a green light. And this one says, well, if there is a green light, there must have been a car. So what could happen in those two? Are they any different, or are they the same? Okay, so let's make the most simple traffic light, one that is always green. Would it satisfy this basic response that if a car comes sometime in the future, the traffic light will be green? Yes, because it's always green, so it simply satisfies that. Would it satisfy the precedence that the traffic light can only be green if there was a car? No, because we might never have a car, but the traffic light is always green, so this one would be violated. Okay. Let's make another very, very simple traffic light, the one that is always red. So would it satisfy the precedence? If there's a green light, then there must have been a car before. No? Why not? The traffic light is always red, so it's never green. So we don't have the problem that we need to see a car first. So it would satisfy that. But the second one, the response, if there's a car, it must turn green, but our traffic light is always red. Not satisfied, right? Because even if there's a car, our traffic light will stay red. So that's, yeah, quite some different behaviors. One could be very, let's say it's costly to turn on a green light. So this one could be very, very wasteful by always making the light green. And this one would say, well, don't waste any resources. Only waste the resources when there really is a need for it. So when there's a car, yes, then you need to turn it on, but otherwise not. But this one could be very, let's say, restrictive because it says, well, you don't even need to turn it on green, right? It doesn't require it. It says only, well, if you do, then you must have seen a car. But if you never turn it on, you're fine. So those are very, very different. Okay. Yeah, then of course you can have this as a chain of events, not only those simple events. Both of them, the precedence and the response, both of them could be chains of sequences of effects. And here are some, yeah, very simple examples. So we saw these, occurrence patterns. So a simple occurrence is, well, the absence, that P is always false, or that P is false. And then we can put it in each of these scopes. So we said the different scopes were globally, or before, or after, or between, or after, until. So if we want to take this same property into the scope globally, that's easy. We just put the globally around it. If we want to put it in the before R, then we have to say, well, if R, so this is the finally, it's just a different notation that they used in the original paper. So people, for linear topologic, they used the box and the diamond. So this is the box and this is the diamond. And the box is globally and the diamond is finally. So you might find this syntax. I think that probably also NuSMV just supports this syntax as like a translation. I don't know. Does it support it? Do you know? Okay. So yeah, not sure. So you could then say, well, the before, you say that if R happens, so eventually R, so if R happens in the future, then we cannot have P until we really see that R happened. So that is putting this same property into all of these scopes. And then similarly, the existence, that P becomes true. So that's like here it's, well, false, here it's true. That's the absence and existence, the duals. Then you can see, well, you just try to encode the same thing again in all of the 5 scopes that we can have in these patterns. Bounded existence gets really, really complicated. So if you say that P is true in some, well, sequences at most 2 times. So this means P holds, then at some point it doesn't hold anymore, then it holds again. And this can happen at most 2 times. So it could hold never, it could hold once, could hold twice, but not 3 times. Then you get more complicated properties. And if you then put them into these more complicated scopes, you see the formulas get very long. So probably nobody would like to no, that's still the before. So this one here, these 2 lines, they are just the before thing. Yeah, so that's, I guess nobody would really like to write those anymore. Yeah, some more examples. Some are a bit simpler, like the response pattern. You just have the globally P implies finally S. So those are quite straightforward. But if it needs to happen between Q and R, then yeah, you need a bit more stuff. And that's these patterns now. So what they did originally, they looked at those, I don't know, 400 industrial specifications. They identified all these patterns. Actually, it happened that some of them never occurred in any specification, but the majority occurred in many specifications. So I think this one is like the response pattern. That's like one that appears in almost every specification, because you always need something like that. The alternative to this is that you would need to know how long it takes for something to happen. But because we have this kind of logical time, this linear time, where we don't consider a time slice to be mapped to, let's say, I don't know, 2 milliseconds or anything like that. We can't really count the milliseconds because we just have this logical notion of time. That's why we usually have to write this eventually, because we don't know how long the computation takes until it happens, but we will require that it eventually happens. Okay, so yeah, many tools that are for different kinds of end users, they will have encodings of these patterns. They do this under the hood. So you will say which scope you want, which pattern you want, whether you want the response pattern or the absence, and then you will say which properties you want, and then they will encode this automatically behind the scenes for you, so that you don't have to write those complicated formulas. But this also means that you're restricted to expressing your specification in those patterns. But still, it's quite powerful, and the majority of specifications can really be expressed just by those patterns. Yeah. Okay, so some applications where people used it for building real systems or analyzing real systems. There are some works, for example, that try to identify the specifics of robotic missions, which are quite different from general reactive systems, right? In those general reactive systems, you talk about variables which are inputs and outputs. And in robotic missions, you usually describe some, higher level concepts of the robot, things it has to achieve, things where it has to navigate. And then they try to see, can we actually find similar specification patterns in requirements that people have written for robotic missions. So they took some 245 mission requirements that they found in the literature and added some additional ones, and then they evaluated them on some mission specifications. They expressed those patterns then in LTL and CTL to build a new catalog. So this is now like a complementary catalog to the reactive specifications, the LTL and CTL specification patterns, but they also need to express them in some logic. So they used again this LTL and CTL logic. And then the user will basically write those requirements, and then they can be translated to different, temporal logics, so pattern to CTL or LTL, and then you can give them to some tools which are, popular in the robotic domain. So in the robotic domain, they use a lot of planners. So did anybody ever see how that works? So usually you have to describe the capabilities of the robot. What can it do? How can it move in 3D space? And then there's like a special language to express this. And you say, well, I want my robot to do a specific thing. So this planner then will go and see what way can the robot actually achieve this. So one very basic planning, that's path planning. You try to find the best path through some environment. And there are many, like, let's say, small planners, for example, I think in computer games, for all those characters that you can't play, they have some planners. How do they move along, stuff like that. So these planners, they are very big in the robotics domain. And then they can also not only send them to the planner, of course, because the planner can then do a plan and they can put it on the real robot or on some simulator. And they also fed it into the NuSMV model checker to check those patterns for consistency. And they could also feed it into a synthesizer where they could then synthesize reactive behaviors for those patterns. So something that automatically implements the pattern. And this is an overview of the kind of patterns that they found. So it's quite different from the patterns that we saw in these like Dwyer patterns, the ones, the LTL specification patterns and CTL specification patterns. They have some patterns which relate to core movement, for example, surveillance. And then in surveillance, they have some sub-patterns about just general patrolling, or in a strict ordered patrolling, so that if you give some rooms that the robot has to visit in some order, the difference between the ordered and the strict ordered is in the strict ordered, it is not allowed to traverse them in any other order. So if you say you have to go from room 1 to 2 to 3, then it can't go from room 1 to 3 to go to room 2. So for example, it could be that if there is a corridor, then in the ordered patrolling, it could use that corridor whenever it wants. But if you say it's a strict order, then it can only use that corridor at the time where it is the right, let's say, order for that corridor to visit. Yeah, and then they have some other patterns for reactions. When does the robot have to react instantly or fast or delayed, stuff like that. This is what they extracted from these mission specifications for robots, and then they built this similar catalog here. And they used nuSMV for testing and validation, so they encoded the mission plans as models. And then they checked their LTL formalization of the mission plans to see whether the mission plans actually satisfy those properties that they extracted from the requirements. And when possible, they also checked the correspondence between the LTL and the CTL encodings. That's not always possible because those two languages, they are incomparable in what they can express. So this is the linear topologic that we know. And this is the computation tree logic, where you can actually quantify over the possible futures that you can have. Whereas in linear topologic, we always say, yeah, there's only one path through the future. And then we have this implicit quantification, whereas in CTL, we can make it explicit. We can say for each point in time, should there exist some future with some property, or should all futures have some property? So it turns out that these two logics then are incomparable, but in some cases, you can express a property in both. So this would be an application, would have been an application to robotics. Another one, which is an application to, well, some reactive systems. This would be in the IoT domain. So for Internet of Things, they have many applications in, well, smart homes, but also public buildings. And some of the IoT devices, they might violate safety and security properties. So what these researchers did is they looked at some, I think this is some kind of smart things market, where they looked at different IoT applications, and you can actually compose those applications. So it's a, I don't know if anybody ever looked at home automation and stuff like that. And if this is still the market, but that's where they published, well, people published apps, and they analyzed those apps, and then they formulated some LTL properties that could actually check safety violations or security property violations. And they found 9 of the apps which already violated 10 properties. So that's like a huge violation. So it violates almost everything it could violate. Well, not everything. Like 10 properties would be the 29% of the properties that they checked. But still, that's quite a bad thing to have some apps violate so many properties. Yeah, and then they also analyzed the combination of apps, and they found more property violations that only happen due to the combination of apps, because maybe on one of your IoT systems you have one app running, and on the other one you have another one running, and then if both are in the same place, they might interact in a bad way, so that one breaks the behavior of the other one, and they would violate more properties. So there would be the general overview. They first had to extract, they wanted to use model checking, so LTL model checking. And for that, they had to extract models from the code. So they had some framework set up with some different code analysis and managed to extract, automatically extract models from some from the code directly. And those models, they are the kind of models that we also would define. So they would be state machines or like state labeled transition systems. So here you are in state 1, you detect smoke, then you're going into this, state 0, then you're going to state 1. If the alarm is then on, you go back to this state, and they're labeled with events or sensor measurements on the transitions, and then actions or properties on the states. So here is a specification for a smoke detector application. So that's, I don't know why you need to have an app for a smoke detector, but apparently that's a thing. So it controls the alarm based on the detection of smoke. So initially you're in the state that the alarm is off. If it detects smoke, then it's in the state alarm on. And if the smoke is gone, it turns itself off again. Which is probably the behavior you know from your smoke detector. You're frying something in the kitchen, this thing goes on, but as soon as the smoke is off, the alarm goes off again, right? Did you have a question?
Yes. Yeah. Does this violation of properties happen only when there are multiple applications?
No, these many violations, they actually found more violations that happen on a single application. So yeah. Which means that these are implemented in incorrect ways, right? The developers of these applications, they made mistakes. So this is the specification for the smoke alarm. And then this is the model that they actually extracted from the code. And this model actually doesn't behave like the specification. The smoke alarm also starts with the alarm off. If smoke is detected, it turns on the alarm. But then the trigger for going back to the regular alarm off state is actually if the alarm is on. So it will turn the alarm on and then notice, oh, the alarm is on, I'll turn myself off, which is not a nice behavior and can be a dangerous behavior. But they found it with their formal analysis of the models that they extracted from the application code. So this is one example that they found where it could be a bug with consequences, right? And then another example that they found is this typical deadlock example where the combination of a smoke alarm with a sprinkler system and a water leak detector actually are interfering. So I think here the smoke alarm detects smoke. It sees that the temperature is, well, quite high, and then it turns on the sprinkler system. But then here, this thing, the water leak detector, just checks is there a water leak with the sensor, and if there's a water leak, then it closes the water valve. So the sprinkler system will be detected as a leak, and the water will be shut off. So this system will not extinguish the fire anymore. And that's something you would then have to write for these combinations. So here, for this system, you would write some specification that says probably that the sprinkler system is active until the temperature is below this this threshold, so that we can be sure that the fire is off. And then you would see that if you combine it with this, you're ending up in a situation where this property of the sprinkler system will no longer be guaranteed. Whereas if you don't have the water leak detector, the property will be guaranteed. Okay, so and they also used the NuSMV model checker. So they first had to express in the source code what are the properties that they want to verify. Then they had some intermediate representation of the models, and for that they wrote properties in, okay, this is actually CTL, this AX, that's for all the paths in the next point in time. So for all the possible futures, in the next step, the valve needs to be on. That's, yeah, a CTL property. And then they use the model checker to figure out whether the properties are satisfied or violated. And they actually, as you can see, these models here, I mean, this one here, it's just very, very few states, very few variables. So they said that it always just took some milliseconds to perform the actual model checking analysis. So that's, yeah, quite good. There are other systems where the model checking analysis takes a lot longer. Did anybody run into timeouts with the model checking for the homework? No? Okay, good. Yeah, then another one, another work, this would be analyzing some other structures, so maybe model-based structures. So this would be some state machine. It's different from those transition systems that we have, but they share some, well, similarities. They have states, but they are much richer. They have, for example, triggers, they have assignments and activities. They have guards where you can only take this transition if this guard is satisfied, or you can take that transition if this guard is satisfied. So anybody knows these from other lectures, state machines, UML state machines? Maybe, yeah. So basically they're quite a rich fragment. They also have hierarchical states. So you could have this state and then you have two, I guess, not sure where these compartments, whether they're in parallel, like two parallel compartments that could be executed. So quite a rich language. And there's a survey that where they looked at how do people actually verify the correctness or different properties of UML state machines. And they looked back, well, basically at a range, I think until 2022 or 23, and then quite a few years back of what did people actually do. Did they give some operational semantics by encoding the meaning of the machines as execution rules, or did they translate it to some other formalism? And many works, they actually, you see, it's very popular to translate it to some other formalism. And this kind of translation, you translate one formalism that is maybe complex or that you can't analyze to another formalism that you can analyze. This is what we always try to do in the second kind of homeworks, where you had to write the code, right? You translated feature models that you couldn't analyze yet to SAT that you could analyze. Yeah, and then you translated maybe some high-level properties of some PC configurations to SMT. And then you translated some, well, maybe consistency or correctness questions about Alloy to, well, Alloy itself, right? So those are all kinds of examples for this translation. You have some problem that you want to solve, and you translate the problem to a tool that can solve this problem for you. And that's, as we see, that's very popular to do. And in many of these cases, people used nuSMV as the target to translate to, because these state machines, they usually have some, well, executions, they have state changes, so it's a good choice to probably try to use something like nuSMV. So in one work, they gave semantics to UML state machines. So they said, well, this is the meaning of these elements by translating them to nuSMV. In another one, they wanted to verify some specification of the state machine, so maybe some properties that this UML state machine really behaves as intended. Again, here, yeah, perform model checking, or then some which look at the collaborations or the, let's say, consistency of the collaborations between different UML diagrams. So you might have some behavior described in state machines, but you might have some behavior described in activity diagrams, and then you want to know whether this collaborative behavior actually is possible. So it could be that one says, well, I'm always turning on the sprinkler system, and then the activity diagram says I'm always turning it off, and then well, those two are not compatible. So you might want to analyze those things, and the way they analyzed it is translating it to nuSMV and then model checking it. Yeah, and another example that's here is the analysis of legal contracts. So this is again a very different thing. The first thing, those embedded systems like the IoT systems or robotic systems, you could imagine, yeah, you can translate them easily to model checking. Then the higher level models to describe software systems, yeah, that's also a lot of computer science, so people probably translate it to model checking. But then here, it's actually also legal contracts. And they took legal contracts, and they also have some time dependencies. Maybe something has to be delivered before it is paid, or if it is delivered and not paid, then you have to go to court before something else happens, right? So all these things, they might be written in legal contracts, and legal contracts are really, really difficult to analyze because they are in natural language, and even the interpretation of the natural language might not be very clear. So what they did is they started to look at these legal contracts, the conditions that they define, and then they said, well, these are all transactions, and we can model transactions in something like a model checker. So they wanted to check conformance of some contract specifications, or the model that they extracted from the contract is what the contract actually does. And then they asked users to write actually the expectations of the contract. And then they could check whether the contract actually meets those expectations. So you can imagine the contract is very heavyweight, lots of details. You translate that to a nuSMV model. And then your expectations, you could write them as LTL constraints. Yeah, and then you can basically model check the contract, whether it really behaves according to those expectations. And of course, they didn't want people to write LTL specifications about the contracts themselves, because nobody would probably like to do that. So they introduced some high-level modeling languages in this tool Xtext. Who was in generative development? You were in generative? No. So that's next semester. Were you in generative? No, nobody. So that's another one, another lecture next semester. We do generative software engineering, where we will also look at this tool where you can actually define domain-specific languages. So it's very different from this lecture because we're not doing very formal stuff. It's more about different tools to generate software, to generate code, generate software. Yeah, and actually this tool we will also use, and eCore we will also use. So yeah, here they kind of combined, well, two of my lectures basically. I mean, I don't know these people, but yeah, and they don't know my lectures, but that's kind of interesting to see that this is actually a combination of those two topics that we're teaching. And Shoaib is also in the generative software engineering lecture, yeah, as the TA. Yeah, so basically, on a higher level, more user-friendly language, they define the contracts. Then they have some translations, intermediate translations, and in the end, they can model check the contracts using the nuXmv model checker. So that's another, well, application of nuXmv. And this is what a generated contract might look like. So yeah, quite complicated. This is what an expected property might look like, that a buyer resumes some suspended delivery by paying some fine. So let's say the delivery hasn't been paid for, so it was suspended, and then you can pay a fine to make it resume. And then this property can be checked. And yeah, it says down here that this property was checked successfully on this contract. Yeah. Yeah, there are some other examples. So, for example, in one of the projects we're doing right now, we're doing something quite similar. There's this concept of behavior trees that people use um, for describing those non-playable characters in games, in computer games, but also they use it a lot in robotics. And we're now trying to translate those behavior trees to nuSMV to then check whether two behavior trees actually describe the same possible behaviors that a robot or a computer player might do. Yeah, I hope we will finish this semester. Yeah, but I mean they're on a good way. So last week this week they demoed, right? And yeah, they can handle some features of behavior trees. Yeah, but that's always the tricky bit, right? You have to understand what does the source language, the higher level language that you want to translate, what do the things there actually mean, and then how would you encode them in this lower level language? So that's exactly all the things we did in the homeworks, right? You have to first understand what does it mean for, I don't know, a signature in Alloy to not have any atoms. And then you need to see, well, how do I encode it? Well, there the encoding was simple, just some extension of the predicate. But yeah, this is always the kind of challenge that we have here. Okay, then some overview of formal methods in general. So the examples that I showed right now, they were all related to LTL, CTL, and nuSMV. But now there are, of course, some literature on how are formal methods, or what's the state of formal methods in general, how is it applied in industry. We saw some examples, more recent examples from companies like Amazon Web Services and things like that in one of the first motivation lectures. Here are more systematic surveys. The bad thing is that these are already 15 years old. So there's no recent survey that I could find which does the same thing. So that's the most up-to-date thing that we know about applications in industry. All the other ones, they are like maybe stories that one company published because they use it. So like this, the analysis at Amazon Web Service, or at Microsoft Research, stuff like that. They published one work, but here what they did is they looked into previously published works, and they also talked to people that they knew. So these guys here, they are quite they're from different countries, and they're quite well known in the, let's say, formal methods community. And so they kind of combined the knowledge and interviewed people about what kind of projects they did applying formal methods in industry. And we can see the different areas that they were applied. So a big area is actually in the transport area. So this could be verification of some train switches and stuff like that. Some in the nuclear area or in defense. Financial also, surprisingly, some financial models are model checked or analyzed with formal methods. So some telecom, you could imagine, those are also very critical infrastructures that they have to maintain. And then, a bunch of others that didn't fit into these categories. And then they asked them, well, what part of formal methods did you use? So the formal methods that we saw in this lecture, it was quite, let's say, maybe biased towards something like specification and modeling. And we looked at different languages, right? We looked at SAT, SMT, Alloy, and nuSMV. How can we model this? There's also other ones based on really proofs and manual proofs. Those are, some other area, or model checking. Well, we covered that as one of our examples. Then there are some other test generation, also parts of formal methods by, again, maybe using SMT solvers to analyze the code and then generate tests that cover the code in some way. So many of these, they use the tools that we looked at, or the languages that we looked at in one way or another. Some are quite different, like this proof stuff. That's we didn't really look at that. That's its own, quite heavy machinery that's needed to do proofs that can also prove things that are undecidable. So logics that are undecidable, we saw some, like first order logic in general. There are many first order logics which are undecidable, and we were always using the fragments that are decidable. But they will even go to higher order logics in those proofs, and then it's a lot of human effort to write those proofs. But the computer will just check that you didn't make a mistake in proving. So yeah. Some examples of proofs are, more popular examples are some verification of a Linux kernel, some real-time system Linux kernel that they fully proved manually its properties. So that's been, I don't know how many years, if it's maybe like at least 4 years that they have been writing proofs about this one system. And yeah, they're still working on it because whenever you want some performance optimization, maybe some better use of the cache memory. So I think in the beginning, they didn't implement any of the caching in the CPU. They just turned it off because it would be too complicated to prove properties about it. And then later they added the caching mechanisms. And then, yeah, you have to prove that the caching mechanisms don't break any of your properties. So yeah, it takes years to write those proofs and make sure they're all working. Yeah. So the stuff that we looked at, they are more the lightweight ones. We write our specification, our model, and then we can model check, and then we get hopefully a good result. And then, of course, one thing that people always say is that, well, either the project fails because people don't know how to use the form methods, or it does fail. And so here they asked, was the project successful, or was the use of form methods in the project successful? And many people really agreed or strongly agreed. So that's very good. Will they use the same or similar methods again? Yeah, similar or even same. So this looks like form methods are great. They always succeed, and people will use them always again. So how come? I mean, there's a huge selection bias, right? So who were the people interviewed? People interviewed were the people who used form methods in projects, right? So not everybody does that, and well, the ones who were interviewed, they probably were successful with their projects, right? That's why they were noticed, right? So, but then they also asked them about the different areas, time, cost, and quality, and how they would assess this. Of course, this is not a formal assessment where you really measure it, because some of these projects, they cost millions to begin with, so you're not going to replicate it with form methods and without form methods just because you want to know. So some of these are, I think that even right now in France, they do a lot on the railway system with form methods, and yeah, that's tons of money that they put in there, and they're not going to do it once with and once without and see if the trains derail more if you don't use form methods, right? So these are all kind of subjective judgments by the people who did the projects or who answered to these studies. So yeah, either they said there's no effect or no data, or an improvement, or a worsening. So here, the lightest color, that's the worsening, and the time got worse in maybe 12% of the answers, and here the cost got worse in 7%. So they judged that form methods actually cost them more time and more money, only in very, very few cases. And in many cases, they said that it actually was improved, that they were faster because of form methods and that the cost was reduced. But of course, there are some where they didn't even assess that or had no way to assess that, or didn't want to make a judgment, I guess. And then here, the quality, yeah, 92% of the responses were that it was improved in the project. But again, I mean, yeah, how would you measure that the quality was improved when this is the only thing you did, right? You can probably get, if your checks failed before and then they passed afterwards, that's a indication that you improved the quality, right? So, but but that's like there are almost no cases where you first verify your system, it works, then you do the project, and then many things fall apart, right? That's not usually not what happens. So again, there could be a bias based on the responses of the people, right? Because that's how do you measure it? You have your specifications, you have your checks, yeah. Then of course quality improved, right? Yeah. Okay, so in conclusion, we see that there are some very successful projects in industry, and also a lot of research going on right now for stuff like IoT or cloud with Amazon Web Services. Facebook also has, which is a bit surprising, but they also have big research labs where they do program analysis because they just have so many different platforms that they want their apps to be deployed to. So they work a lot on making sure that code doesn't break. And then, of course, this is stuff that they can give out to the general community, right? That they don't only internally keep, because they involve researchers from many universities. So they like give this stuff back that other people can build on it and improve software engineering in general using those 4 methods. Yeah, and if you're more interested in doing some, let's say, more literature-based studies or some research, then we're going to offer, I think, next semester again a seminar, very likely, which is 3 credits. So that's a bit a strange number, but it's basically like those kind of lecture meetings, and then you have to do some report and write some report based on some literature research. So those credits, they come together due to a lot of literature research that you have to do for these meetings. Yeah.
Is this going to be a replacement for advanced topics?
Yeah, that's the same basically. Yeah. So we had this last semester. We had this advanced topics in software engineering seminar. Yeah. It will be very similar because we will have those workshops where the skills workshops. So what we did last semester, we had like some. If you want to do a literature study on any topic, not only for methods but any other topic, there are some like, let's say, skills that you have to learn. And if you want to write the seminar paper, you have to learn how to write maybe research questions, how to evaluate research questions, how to find literature, how to judge literature, how to classify literature. So for that, we divided this seminar into some skills workshops. And then those workshops, they would usually be based on one student presenting the topic of the workshop. And that's then part of the marks that you get for the seminar, because you're responsible for, let's say, presenting what are good research questions or how to give a good seminar presentation. Like each person in the beginning will be given one topic that they then have to present, which is like a meta topic, because it's a topic that everybody needs to know to do a good seminar, but it's not yet related to the, let's say, the scientific topic of the seminar. So you will have this meta topic, and then you will have a scientific topic that we will also develop. And in these skills workshops, there will be one on research questions, right? So for your scientific topic, you need to define research questions. So then once we have learned what are research questions and how to write good ones, you will do that based on this knowledge to basically write a research question for your scientific topic. So it's like a, skills plus scientific thing seminar. That's why it's 3 credits. Yeah. You were there last semester, right? Yeah.
I mean, don't you think it would be better that this seminar is shared in a way that an article can be published in a group? I mean, not only a person by the end of the semester, because it would really be difficult with other courses for one individual to do that.
I mean, it's 3 credits is.
I mean, it's not about the grade.
Yeah. So you mean to have some, let's say, working in pairs on this?
I mean,
Yeah, maybe.
I mean, if it's going to be similar to the
Yeah.
seminar
Yeah.
of last semester, so maybe we can take use of those information or those seminars that people did last semester
Yeah.
and go like faster. I don't know. I'm just
I think, well, I think we, yeah. Okay. So wait, let me first finish
yes.
this and then we can talk about the seminar. Yeah, so are there any more questions about formal methods right now? Then what we will have on the schedule, this is the next one. Wait, no, that was already passed. Yeah, we moved the help session to next week. So we will have another help session, and then we will have the intermediate presentations. And the intermediate presentations, there will be 10 minutes of presentation for each group, plus discussion and feedback. So yeah, maybe some 5 minutes for each group, right? Then we are at 5 times 15 minutes. Should still fit into the session. Okay. Yeah, and intermediate presentations, we will put some assignment where you can upload them so that we have them for reference for the day that you present them. Okay, so if there are no questions right now, then that's it for today.